Notes today. More vocabulary. So, we're going to finish all the notes today. We are just going to skip all of this stuff. Well, we're not going to skip all of it. What I do want you to know is this term, scope of inference. All that means is what kind of conclusion can I make and to who? So we've talked about the reason you take a sample is you want to know something about the population. And so the question is, when I have my sample, can I make a conclusion about the population? And what kind can I make?
We didn't finish the last two questions. It's fine.
Thank you. I remember that. I know we didn't finish the last two questions. We're just going to skip them and cover them in here. Okay, so there's two big questions. When I make my conclusion, does it apply to the whole population? And can I conclude cause and effect? Those are the two big things. So if we move down, before we do this example, here are the two pieces that you need to know. First one, can we make a cause and effect conclusion? Yes. For what kind of studies? It's one of the very first things we talked about. Experiments. So you can only show cause and effect for experiments. The first example we looked at was taking vitamin D and whether it affects your health. And we said we cannot conclude that taking vitamin D causes an improvement in health. Remember how we said there are all those other variables that are possibly involved? Okay. So observational studies, on the other hand, they can show that there is a correlation or there is a relationship between two variables, but they cannot show that one variable causes the other. So once we know what kind of conclusion we can make, can we conclude cause and effect, yes or no, we want to know who does that conclusion apply to. If it's a random sample, then we can generalize to the population. A random sample is likely, it's not guaranteed, it's likely to be representative. So if we have a random sample, it is likely that that sample is representative of the population. That's why we can generalize. Okay, if it's not a random sample, so if you just take anybody that volunteers to be part of your study, then the conclusion applies to those volunteers and people like them. So that's what you're asking yourself. Was it an experiment? Yes or no? Was it a random sample? Yes or no? Okay, so we're going to look at the four cases that are above. This relates to some of you. Many students insist that they study better when listening to music. As teachers, sometimes we doubt this, and we think that maybe listening to music can actually hurt academic performance. So here are four possible study designs. And what we're going to do at the end of a semester or a unit or something, we're going to look at students' GPA. So this is the question down here. For each design, let's say that the GPA for students who listen to music while studying was lower than the students that didn't listen to music. What can we conclude? And so what we're going to ask, can we conclude cause and effect, and who does that conclusion apply to? So the first one, get all the students in your AP Stats class to participate in a study. Ask them whether or not they study with music on and divide them into two groups based on the answer to this question. First thing, study one, is this an experiment? How do we know it's not an experiment?
There's no random selection, you're not assigning treatments.
Okay, you're not assigning treatments, right? You're taking the people and asking them, do you listen to music? Or do you study while listening to music? So, not an experiment, we can only show correlation, only show a relationship. Was it a random sample? No. All we're looking at is the students in this AP Stats class. So, if I ask us, what kind of conclusion can we make? Here's what we can say. We can show a relationship between listening to music while studying and GPA for these students and those like them. Now, I'm skipping a lot of words. Hopefully, if you were doing this, you would provide more context. So I shouldn't say music, I should say listening to music. Okay. So then 2, select a random sample of students from your school to participate in a study. Ask them whether or not they study with music on and divide them into groups. Okay, study 2, can we show a cause and effect? No. Again, we did not randomize treatments. We did not assign treatments to people. Who does the conclusion apply to? Can I generalize to the population? Was it a random sample? Yeah, random sample. Now, who is the population? Who can I generalize to? Can I generalize to all students? No. Who can I generalize to then? Students at this school. Okay, so again, correlation for all students at this school. If this was on your homework or a test, that's not enough. Just saying correlation is not enough. You would need context, but I'm being lazy. Are we okay so far? Yeah? Okay, 3, get all students in your AP Stats class to participate in a study. Randomly assign half of the students to listen to music and the remaining half to abstain from listening to music while studying. Can we show cause and effect? Okay, Michaela, why am I allowed to show cause and effect?
Because you're assigning the treatment stage.
You're assigning the treatments. Great, thank you. Kendall, can I generalize to all students? No, I'm only looking at these students, not a random sample. Okay, now I'm going to write out in full detail what we just said. Going back to the original question. If those who listen to music have a lower GPA than those who don't, what can we conclude? We can conclude that listening to music while studying causes a decrease in GPA for these students and those like them. Do we get the idea? Yeah? Okay. Questions? Okay, one thing I want to be very clear of is a lot of people use these 2 words interchangeably. Random and randomize. And I cannot stress enough that those are not the same thing. So we're going to write down what they mean, but I need you to like star, bold, make it very clear that these are not the same. They have 2 radically different meanings. When we say random, we are referring to a random sample, which is how the sample was chosen. When we talk about randomize, that means randomly assigning treatments. When we randomize treatments, we have an experiment. So it does not make sense to say we have a randomized sample. That doesn't make sense. You don't randomize a sample. You have a way that you chose your sample, and then you have a way that you give treatments. But there's no such thing as a randomized sample. So we should not be using these in the same sentence because we misuse them often. I would say, yes, I have a random sample so I can generalize. Also, treatments were randomized, so this is an experiment. Okay. Questions before we look at the next example? Okay, next example is one that you are going to do. So we are going to take a look at SAT prep courses. So students tend to enroll in prep courses to improve SAT or ACT. Let's say that 20 students who have taken the SAT have volunteered to participate in an experiment comparing online and classroom prep courses. First thing I'm going to ask you before we even design our experiment, who does our conclusion apply to?
Is it the 20 students and those like them?
Okay, our students volunteered, so these 20 students only, and people like them. What you're going to do is you're going to do question number 1, design an experiment. So I'm going to give you 5 minutes. I want all of the steps that we followed before. How are you going to randomize? What are your treatments? What are you measuring? How are you going to compare? And then remember, the last thing I want you to include is what are you going to control? So 5 minutes with the person next to you, and then we'll come back and go over. First thing that I noticed when I was walking around, describing the completely randomized design. What some of you said is use the hat method to assign 10 people to the online course. That's not specific enough. It has to be specific enough so that I could carry it out. Can anybody tell me how they used the hat method, just like the first sentence or two? Matthew?
You said we would write all their names on slips of paper, put them all in a hat, and then mix.
Beautiful. Thank you. Did we all mix? Please don't lose credit because you forget to mix. Okay. And then I would say something like, draw 10 names. What do I have to make sure I say? Without replacement. And something like those are the online people. And then maybe the remaining 10 are in the classroom. You should have written more than this, right? I'm just trying to be quick. Okay, and then what did we decide to measure? What did we measure, Augie?
The difference between volunteers and prior SAT scores and new ones.
Okay, so did we all decide to do a SAT test and then do another SAT test? You didn't have to. At the end, you definitely need a test, like after 3 weeks or however long this course is. Okay, so we're gonna give everyone a test. And then in our compare, were we specific? Something like compare the average or the mean improvement for the two groups? What are a few examples of things that you guys decided to control? Okay, I think that's a good idea. So all of the students see like the same topics?
Yeah.
Okay, great. Alex?
We said course length and then like instructor.
Okay, they're all taking the same length of course. They're all using the same instructor. Anybody come up with anything else, Colleen?
Except the time and day that they need.
Okay. Time and day. And I think there's a bunch more you can come up with. Augie, what were you going to say?
I was going to say that they take the same test.
Yeah. Same test. Evan, is that what you were going to say?
I was going to say, if they're doing like a pre-test, like one before control, they should take the same practice test.
Great. Okay, that was your experiment. So when it says completely randomized design, that's what it means. Okay with that? We're going to talk a little bit more and then we'll take a break. Again, I'm going to try to be efficient, so we might be skimming these a little bit. Now, let's say out of those 20, 10 are in pre-calculus, 6 are in algebra 2, and 4 are in geometry. What issue could there be? Hopefully we can see if we split them up 10 and 10, isn't it possible that the 10 pre-calc kids would end up in one group and that the 6 algebra 2 and the 4 geometry ended up in a different group? Right, and so maybe all of these ended up in the online group and all of these ended up in the classroom group. And then any difference in their SAT scores, do we know why that occurred? What's the vocab for that? Confounded, right? We say class is confounded with type. Okay, so there's 2 different ways that we could address this. First way is we could eliminate some of the kids. Or some classes. So for example, maybe we decide to eliminate algebra 2 and geometry. Now, if we do that, what is the consequence? So we only have pre-calculus kids, so we got rid of that extra variable. But what is the consequence in terms of our conclusion?
There's a smaller sample size, so there'll be more variability.
Okay, great. Number 1, smaller sample size, there's going to be more variability.
It only applies to the pre-calc.
Okay, that and our conclusion would only apply to the pre-calculus students. So it's an option. Is it the best option? I don't know. What we're going to talk about before we take our break, so this is like another page, but we'll go through it quickly, is something called blocking. So that's what we're going to talk about next. Blocking is a way to deal with confounding variables. Okay, we're not going to do this, but here are all of the 20 students, and it tells you the improvement in their score and what treatment they got. What I was going to have you do is make 2 dot plots for the classroom and for the online. And what you would end up noticing is that they look very similar. So if we looked at all 20 students as a whole, we would say there's probably no difference in the classes. But then the question is, what happens if we look at the pre-calculus students separately from algebra, separately from geometry? And that's what you have on the next page. So this is maybe a little bit hard to see, but now we're differentiating. These squares are the students in geometry, the circles are the students in algebra 2, and the triangles are the students in pre-calculus. So if we look at as a whole, it looks like maybe there's a little bit of improvement. But what happens when we look at those 3 groups separately? Do we see that the geometry students scored higher in the online? The algebra students scored higher in the online? The pre-calculus students scored higher in the online? You guys with me? What does this remind you of when you're taking a population and you're breaking it into groups? Stratifying? Okay, this is called blocking. You're like, but it looks like stratifying. Yeah, they're pretty much the same thing. Just different vocab word. So we're going to write down a few things and then we'll take a break. Okay, so that's what all of that said. So question is, why do we block? So first reason, it accounts for sources of variability. And that variability comes from confounding variables. Like stratifying, what was the main reason that we stratify? Augie, say it again. Less variability. Less variability. That is the big one. So it increases our chances of finding convincing evidence. And we'll talk about what that means, convincing evidence, in a little bit. Okay, how do you determine which variables to block by? The same way you would do in stratifying. You are looking for variables that are strongly associated with the response variable. Within blocks, subjects should respond similarly. But different from the other blocks. So again, it should be exactly like stratifying. Now, I think I told us this was stratifying. Some of you said, how do I know I need to use a stratified sample? And I said, normally you don't unless either you're told to or you're told that there's some other variable. I do not block in an experiment unless I am presented with a very, very obvious choice of blocking. So let's say that we were looking at reaction to a medication. So I'm using 2 different medications and I want to know how do they affect blood pressure. I'm not going to block because I haven't been told any reason that I should block. But then the question might say something like, we're concerned that men and women will respond differently to the medication. What should you do? Okay, very clearly they're telling you there's this other variable we need to control. You're going to block. So it would be similar to what you did here. You have women in one group, men in another group. Okay, last thing before we take a break. Blocking is the term that is used for experiments. Stratifying is used for observational studies. That's it. That's the only difference. So they are practically the exact same thing. All you have to remember is you stratify in, not even really an observational study, in a survey. When you're sending out a survey. Okay, so we have 2 last examples to do and 1 or 2 other things to talk about. Are there any questions about blocking? Okay, so look at this next example. A popcorn lover wants to know if it is better to use the popcorn button on her microwave or use the amount of time recommended on the bag of popcorn. To measure how well each method works, she will count the number of unpopped kernels remaining after popping. She goes to the store and buys 10 bags, each of 4 different varieties of microwave popcorn, for a total of 40 bags. Outline a randomized block design. Okay, so again, keeping in mind, blocking is just the same as stratifying. What are we blocking by then, if you think of it like stratifying? What are our groups going to be? Come on, guys. Thank you. Type of popcorn. Okay, so this is called a randomized block design. That is different than a completely randomized design. If we were doing a completely randomized design, we would take all 40 bags and split into the 2 treatment groups. Why is that maybe not the best idea? So if we took all 40 bags and randomly assigned them to 2 different treatment groups, why is that an issue? Not an issue. Why is it maybe not an ideal design? Do we see that the groups might not be the same? Right? You might end up with like the movie, butter, popcorn in more in one group than in the other. Okay. So that's why you're not going to use a completely randomized design. In a case like this, where it is very obvious that you should block, you should block. So I'm not going to outline the entire design. What you would do is you would take the 10 movie butter bags and you would split them 5 and 5. And then you would do the 10 light butter. And you would split them 5 and 5. So on and so forth. So then, out of these 5 and 5, 5 get the button, 5 get the time. We would do this with much more detail, though, than I'm doing, right? Like, if you're doing this in your homework, please tell me we know that I have just putting, like, not even bare bones here. Okay, so then ultimately, you're going to have kind of 4 different conclusions. So we would look at the average for the movie butter, averages, and then we would look at the averages for the light butter, and then we would look at the averages for the natural. So the movie butter, we would compare the popcorn button to the time on the bag. The light butter, we would compare the popcorn button to the time on the bag. For the natural, same thing. Popcorn button, time on the bag. Bless you. Okay, so I will tell you what I would do in this case, hat method wise. I personally probably wouldn't number the bags. What I would do is, if you're using the hat method, which you know is my favorite method, I would have 5 slips that say button and 5 that say time. So then what I would do is I would have the popcorn bag and I would pick a slip for that popcorn bag. And the reason I would do this is I can use these same 10 slips for all 4 kinds of popcorn. So if you were actually describing this, what you would do is you would describe fully for the movie butter. I'm going to write 5 slips that say button and 5 slips that say time, and I'm going to mix them in a hat. You describe all that for the movie butter, and then you can say, do the same process for the other 3 kinds of popcorn. You don't need to write it again. I know I'm throwing a lot at us. Does that make sense? Okay. And then, again, why do we do a randomized design? We would say 1, to control a confounding variable. So I'm going to say control a confounding variable. And 2, the bigger reason is we're going to have less sampling variability. Okay. One more type of design, a matched pairs design. So a matched pairs design is a specific block. And a matched pairs design, bless you, there are only 2 subjects in each block. So one very common example is twins. Taking twins, have one twin get one treatment, one twin get another treatment. Or another example is using the same person. So for an example of the same person one, I think we've all seen when you've been outside, have you ever been in a group and some people in the group get attacked by mosquitoes and other people get no mosquito bites? Okay, right? We've all seen that. So if we want to compare two different mosquito repellents, you might decide to use the same person. And so that person would get one repellent on one arm, other repellent on the other arm. So that person is getting both treatments. Now, what is important to remember here is in an experiment, we have to randomize. So we have to randomize those treatments on this person. So what that would mean is we have to randomize which arm gets which treatment. Again, you only need to do this if you are specifically told design a matched pairs experiment. Okay. We don't have a ton of time. We're going to do this example. This is what we're going to end with, is this last example. This is very similar to one you have on the homework. Over the years, the percentage of births that are planned cesarean sections has been rising. Because doctors can schedule these deliveries, there might be more children born during the week and fewer born on the weekend than if births were uniformly distributed throughout the week. To investigate, Miss McDonald and her class selected a simple random sample of 73 people born since 1993. Of these people, 24 were born on Friday, Saturday, or Sunday. So let's just stop right there. If we stop right there, 24 out of 73 were born on a weekend, if we're considering Friday the weekend. That ends up being about 0.33. So about 33% are born on a Friday, Saturday, or a Sunday. Okay, in a perfect world, it should be 3 out of 7, right? 3 out of 7 days. 3 out of 7 is about 0.43. Okay, so what this is arguing is people are going to be planning their cesarean sections, so maybe there's less people born on the weekend. Is that the case based on the sample that was taken? Right, less people born on the weekend, right? We expect it to be 43%, but actually it was 33%. Does that definitively mean that there's less people born on the weekends? No. Okay, so here is what is really important. What we are trying to figure out. We are trying to figure out if we got this 33%, because in fact it's true that less than 3/7 are born on the weekend, or did we just happen to take a sample where less people were born on the weekend? We agree that can happen, right? We just happen to end up with a sample where less than 3/7 are born on the weekend. Okay, so determine if the data provides convincing evidence. So we want to know, is it really in fact less than 3/7? We have this dot plot. This dot plot is 100 samples. So what this does is it takes a population of, 1 million people, where 3/7, 43% of them were born on the weekend, and it takes a sample like we did of 73. And it plots how many people were born on Friday, Saturday, or Sunday. So this represents one sample where 22 people out of 73 were born on a Friday, Saturday, or Sunday. This is an entire sample where 23 people were born out of the 73 on a Friday, Saturday, or Sunday. Do we understand what this is saying? Okay. So first thing, how does this show us sampling variability? It shows us that we can get different values for samples taken from the same population. Even if 3/7 of people were born on the weekend, in a sample of 73, we could get anywhere from 22 people born on the weekend all the way up to 40. And this last thing, do we have convincing evidence that less than 43% were born on a Friday, Saturday, or Sunday? So here's what I want you to write down. Convincing evidence, that is also called statistical significance. Do we have statistically significant results? Okay, here's what you're doing. You're figuring out where did ours occur. So 24 occurred here. So really we're looking at 24 and less. Okay, was it likely to get 24 on this dot plot? No, right? It was not very likely. What that tells us, since we did in fact get 24, is that our results are significant. They're significant. We do have convincing evidence because it's so rare that we would have actually gotten those results. So is there significant evidence? Yes. We're not going to explain because I don't have time and I want to make sure you guys get to lunch on time. You have one of these in your homework. It has a video attached to it. So if you remember, there are videos for the 4.2 and 4.1 homework.